So before we begin, are there questions from homework 6? I'm going to talk about a little hint for the problem 2. And for problem 3 also, I saw some people trying to use the symbolic math in MATLAB. But problem 3, there should not be any symbolic algebra going on in your code. For problem 3, it's about the Q4. All you need to do is follow this computer implementation note that I gave you right here. So I laid out pretty much all the steps that you need to do for a computer implementation of a Q4 element. So take a look at this, and all you need to do is basically calculate whatever quantities that you're calculating. You have to calculate at each and every Gauss point. So in this case, there's a 2 cross 2 Gauss point, meaning we have 4 Gauss points. So all this, you need to loop over each and every Gauss point. Okay. So are there any questions from any of the homework problems? Okay. So let me talk about this hint for problem 2, especially for triangular elements in general. So we've been using these area coordinates, and so for T6, doesn't matter what shape the actual element is. The quote-unquote parent element for the for the triangles for T6, these are the shape functions that we derived in class in terms of L1, L2, L3, and there is a corresponding sort of relationship that this is just like the isoparametric map in the Q4. So this is, you can think of these 3 relationships as the isoparametric map for the triangular element from the parent domain to the actual domain. This is relating L1 to X and Y. Similarly, L1, L2, L3 are related to X and Y from the parent domain to the actual domain. And here I'm distinguishing this a little bit. Probably, I think some of you got confused that this L1 is not equal to this N1. This L1 is equal to the shape function 1 for the underlying 3-noded triangle. So that's why I'm denoting this with N1 T3. And I think this is on the last page of your handouts today. So once you have these relationships that convert from XY to L1, L2, L3, your objective is to set up all these B matrices. And to set up a B matrix, you can see that what you need is derivatives of these shape functions, not with respect to L1, L2, L3, but with respect to X and Y. So if you want to do derivatives with respect to X and Y, what you need is the chain rule. So this is also something that we did in class. And for all triangles where the nodes are equally spaced, doesn't matter how many nodes it has inside. So this is a T6 triangle, it can be T10, whatever, T15. This is related to the Jacobian of the triangle. This is going to be a constant. Doesn't matter how many nodes are there in the triangle. So since this is constant, this is in terms of L1, L2, L3. Therefore, all these B matrices are going to be in terms of L1, L2, L3. There's no X and Y. There's no X and Y in here. Okay. And in order to calculate, I think the biggest trouble that most of you seem to have was how to set up this matrix. This matrix inside is going to be a 12 cross 12. And each term of those 12 cross 12 was a nice big polynomial expression. Okay. So how do you integrate that? A good way to do that is like in this way. So you have your 12 cross 12 integrand matrix. Okay. You set it up in terms of 1 through 6. Just have a loop that loop over I that goes from 1, 2, 3, 4, 6, and loop over j that goes from 1 to 6. So that's essentially a loop over alpha and beta. So what we are trying to do is calculate this small circle or this small square portion of this entire matrix. So after that double nested for loop is done, you will have this entire matrix. So what we've done now is converted the problem from this 12 cross 12 matrix to a small 2 cross 2 matrix. And we know how to calculate that small 2 cross 2 matrix, this k alpha beta. This is the small portion k alpha beta. It is uh, this B matrix, the specific columns alpha that are related to these ones from the B matrix, and the corresponding beta that might be somewhere else in the B matrix. You pick those columns out, and you do this multiplication: B transpose D B. Okay. So once you do this B transpose DB, the output of this is going to be what? What is the size of this matrix going to be? 2 cross 2. And this is the same 2 cross 2 that goes in here pretty much. But the thing to note here is that this 2 cross 2, it is very easy to calculate. You don't need to ask MATLAB to do symbolic math and all that stuff for this. What you can do is, you already know what N1 is in terms of L1. You take the derivative of of this with respect to L1, you will have 2L minus 1. And similarly, what you are essentially trying to calculate is the types of products that you will have. So n alpha comma x multiplied with maybe n beta comma x or y. So those are the permutations and combinations of all the different types of products that you will have in this 2 cross 2 matrix, where each of those terms will be at most a quadratic equation, at most a quadratic expression, which means that since we are using T6 shape functions, these shape functions are at most quadratic. So in any of these 4 terms, each of these 4 terms might actually look something like this. So let's say this is the term that we're talking about. It might have terms which have a constant, something with related to L1, L2, L1 square, L1, L2, and L2 square. So this is a polynomial of at most a quadratic degree. And this term right here might look something like this. So this you can actually integrate using your factorial formula. So instead of doing symbolics with MATLAB, where you will get a huge long expression and then trying to extract the exponent of that expression and trying to use the factorial formula, you can do most of these stuff. I mean, yeah, I agree that once you have a 12 cross 12 matrix, it looks a little daunting to have to integrate everything by hand using that factorial formula. But what I'm trying to tell you here is, you don't actually have to integrate all the 12 cross 12 terms. Go to a specific small square, which is a 2 cross 2. Each one of those entries in the 2 cross 2 is related to alpha and beta. You can use your MATLAB code to implement it in terms of a loop, that goes on 1 to 6 in alpha and 1 to 6 in beta. And then you don't have to do any symbolics. The code will be very fast, and this is how actually people implement it in higher order triangular elements in finite element codes. Another option is, now that the other option is the same as what you've been doing for Q4. Go to just like we had Gauss points in our Q4, we have Gauss points in this triangle, and those Gauss points are listed in the same sort of table in your books that I gave you in the notes. I gave you a table of Gauss point locations in these notes, right? You have a similar sort of table which has Gauss point locations for a triangle. You know that what you want to integrate is a quadratic polynomial. Just choose 3 Gauss points over. You will get an exact expression for the integral. So you don't have to sort of overdo the extraction of the indices I, J, K and use those things. But and I saw that some people actually did it using XY coordinates, and XY coordinates will work only for this problem because your triangle is oriented along XY, which is okay. If you did that, that's fine. But in general, the better way to do it is this. So any questions on this? How many of you have actually finished this homework? Okay, quite a few. All right, so if there are no other questions, then let's talk about something that we missed last time. We were talking about this patch test. So, and I mentioned to you that this patch test is used when you try to develop a new element. The elements that we have been talking about, the elements that are available in Abacus and other finite element software, they have already been tested. So you don't actually need to do a patch test unless you are developing a new element. And the way to do these patch tests, the most critical idea is right here. Let's say you have some domain and you impose a state of through the boundary conditions, you impose a state of constant strain over this problem. So the idea is that these internal nodes should move in such a way so that that state of constant strain is exactly reproduced in every element. If it is exactly reproduced in every element, then you can say that your element passes the patch test and it is a good element that will converge when you refine the mesh. If it doesn't pass the patch test, then you cannot say that your error is within h square of something. Okay. You might get instability, you might get locking. Those are lots of different types of problems you can encounter if your element does not pass the patch test. So I think there was something about convergence that we missed last time, right here. So these are some of the, without having proved any of this, we are going to just accept these sort of error measures. So we talked about how you can set up something called an error equation. So this is an error equation. For any finite element formulation, you can set up this sort of an error equation which actually measures, this is the finite element solution that you get after you do your KD minus F and all that. This is the finite element solution that you will get. And let's say somehow you know the exact solution. So finite element solution minus the exact solution, that is the error in your solution. You take that error and you apply your weak form for any virtual displacement. What this is saying essentially is that the energy of the error within the finite element space is going to be 0 with respect to any virtual displacement. So what that says is that given this set of functions, you have assumed now that this is your finite element space. Given this assumption, whatever solution you are going to get from KD minus F is the best possible solution. Okay, but that is true only within this space. In general, over the entire continuous space, this is not 0, and that is the whole problem of how to estimate how much error there is between the finite element solution and the real exact solution. And so without proving, we just came up with these measures. This is the energy of the error, or the error energy. It's the same thing. This is going to be proportional to h to the power 2p. So for linear finite elements like your Q4 or T3, P is 1. Error in the energy is going to be order of 2. Similarly, error in the displacement is going to be of order HP plus 1. So again, that is 2. Error in the strains and stresses, that's going to be order HP. So these are things that you can actually plot from the homework 5 and homework 6 problems that you did and verify. So just to verify, I had plotted this, but so in general what will happen is that if you have some sort of an error, it will be proportional to C to the power C times H to the power Q, in which case if Q is greater than 0, we say that this method is convergent, that it has accuracy with order Q. So the idea is that when we talked about this last time, that convergence is equal to consistency plus stability. So once you have consistency plus stability, then you have convergence. And once you have convergence, you can talk about accuracy. If you don't even have convergence, you can't talk about accuracy. So when we say that our method is accurate up to whatever P plus 1 or Q, we are saying that if you decrease the size of the element, our accuracy will increase 4 times. Okay, so if your method is not consistent or if your method is not stable, you cannot talk about accuracy. So just to give you an example, this is the finite element mesh that you used for homework 5. So you got many different, for 4 or 5 different meshes, you got the value of displacement, right? So what I'm plotting here is on a log-log scale. This is also something that I asked you to plot for homework 6. So if you remember, the biggest element size was the coarsest mesh. What was that? Maybe 0.5 or something? 0.5 was the element size of the coarsest mesh. So log of that would be what? Log of whatever. So that is so that is some point here. Okay, and as you keep on refining the mesh, your error keeps on going down, and your element size is also keeps on going down. So from this point, as you refine the mesh, you get to this point, and so and so and so on. And you can see that this is the result that you get from your finite element program. And the slope of this line is actually 2. And that is what I wanted you to plot to see that actually this relationship holds. That as you decrease the size of the element, your error in the displacements is going to go down with the power 2. And this is a very good way of checking whether your element or whether your implementation, whether your program is correctly implemented or not. If there is even a slight mistake, this order of convergence will get screwed up very badly. So in this case, actually, you can see that towards the end, it is also sort of increasing in this. So this is the minimum possible convergence rate that you can get. There are different types of methods that are called spectral finite element methods. In those methods, you can actually gain much more accuracy, but you have to use very specific shape functions. So this is just to give you an idea of how you can improve the performance of your finite element codes. Okay, so this is what we were missing last time, and here's a little bit of a discussion for stability. So the idea for stability is that in the end, when you are trying to solve this equation needs to have a unique solution. It needs to be well conditioned. So anybody remember what the condition is for a matrix? What is the condition number of a matrix? So let's say kappa is the condition number of a matrix K. This is nothing but the maximum eigenvalue divided by the minimum eigenvalue. For any matrix, if you have if you calculate this quantity, this is going to give you a measure of the conditioning of this equation. If the condition number is very large, let's say 10 to the power 7, 10 to the power 10, whatever, a large number, then large condition numbers are bad, which means that you cannot accurately solve this equation on a computer, because computer has a finite precision. It stores up to maybe 14 digits, right? If your condition number is of the order of 10 to the power 10, you've already lost 10 of your significant digits. So it is very difficult to solve badly conditioned matrices, and that's the type of warning that you get sometimes in MATLAB, that your matrix is badly conditioned, right? So the idea is that for stability, your stiffness matrix K needs to be well conditioned. So this number needs to be small. What is the minimum possible number that you could get for a condition number? 1. And for example, if you have an identity matrix, the maximum eigenvalue is 1, the minimum eigenvalue is 1, your condition number is 1. It's a perfectly well-conditioned matrix. So that is the best case scenario. Obviously, from finite elements, we do not get an identity matrix for K. So in general, this number should be of the order of 10 to the power 2, 10 to the power 3, something like that. So the idea is that how to make sure that when you assemble all your small element stiffness matrices into a big global stiffness matrix, how do you make sure that your k remains positive definite? So the main trouble with this is that if any of the eigenvalues goes to 0 or becomes close to 0, then the condition number goes uh, becomes very large, and that's not a good thing. So what we want is that when we assemble all these stiffness matrices and when we do the boundary condition, then how to make sure that this thing remains small, remains positive definite. And that is the area of what is called stabilized methods. Just to give you an example of what these stabilized methods do, I will take this global stiffness matrix and I will just add some alpha times identity. I just told you that identity is a perfectly stable, perfectly well-conditioned matrix, right? So if I add these two, it becomes well-conditioned. But the trouble is that you cannot just arbitrarily add some alpha times identity, because your solution will change, right? You cannot just say that I'll change my stiffness matrix, add a little component, and now it is stable, but the solution that you're calculating is not correct. So these types of methods are not consistent. So even though you have made your method stable, you have lost consistency. Therefore, you will not in general have convergence. Okay. And there are different types of other robust methods that people have come up with, where you can stabilize your K matrix. You can change F a little bit so that D does not change, so that the underlying problem that you are trying to solve is still the same problem. Those types of methods actually require quite a lot of mathematical functional analysis. And this functional analysis is a sort of advanced field in people who do graduate studies in mathematics take these kinds of courses. So we will definitely not get into that, but this is just for your information that you can. I think there was some post on the forum where how do you make sure that your stiffness matrix is stable? How do you make sure your solution converges? So these are the two types of criteria that we use to make sure that our stiffness matrix converges. All right, so last time we just barely started this extension to 3D, and I told you that there's nothing much new about this extension. The same type of formulations that we've been developing for 2 dimensions, it's just a little more generalization of the 2-dimensional to 3 dimensions. So here, what I'm showing you is this problem. Here is a beam. It has a small notch in it. It is a 3-dimensional. So again, I should not call this a beam because we'll talk about beams later. This is a 3-dimensional cantilever domain, let's say, with a notch. This is you're applying a traction at the end, and this is fixed at the fixed at this point. So the stress distribution, if you plot the axial XX stress, that looks something like this, because there is stress concentration. Whenever you have a sharp edge in your domain, you will have a stress concentration like this. So a different problem is something like this. You have a cube, and let's say you are imposing, I don't know if this came out right on your handout, but you are imposing a torsional mode to this cube. It is fixed at the bottom. Your domain is omega. This is the fixed boundary. This is the free boundary. And sort of the stress and the displacement is plotted for you. So the way we try to solve these problems is exactly the same. You take your governing differential equation, dot product it with a virtual displacement. In this case, this is a 3×1. This is also a 3×1. And what you will have is a scalar, right? This is a dot product of a vector with another vector. So the output should be a scalar. And this needs to be true for all virtual displacements in the H1. Now this H1 is a space in omega. What that means is, actually in 2 dimensions we were able to plot the shape function for our triangular. Let's say you have in 2 dimensions you have a triangular domain. You can plot the tent type shape functions and visualize them in 3 dimensions for 2-dimension problems. But when you come to 3 dimensions, it is not possible to plot the shape function. The only way you can do that is using these types of colors. But the ideas remain pretty much the same. You have to make sure that your element is continuous and smooth within the element, and it is compatible across the element boundaries. So those are the types of conditions that you have. Once we have this equation, you do integration by parts, and in 3 dimensions, you use the divergence theorem to do that. I've laid out the steps for you. U dot div sigma, that's this term right here. And this term is equal to this term minus when you take this to the other side. So what you will have, if you substitute for this part, you will have this thing right here and minus this thing right here. Okay. So this is the same thing that we derived for the 2-dimensional problem, and pretty much the exact same derivation we are following here. We just have to keep in mind that each of these quantities are 3 cross 1. Now this thing is like the boundary term that you used to get from your 1-dimensional integral, right? When you do integration by parts on your 1-dimensional integral, this is the boundary term. So the boundary term, you can use divergence theorem to convert it to a boundary integral, which means that you take this quantity and dot it with the normal. So this n is the normal to this domain. So like this is your domain. At every point you will have some normal vector. So this, you take this quantity, dot it with your normal vector. This is your boundary term for the 3-dimensional case. And the rest of this of the stuff remains the same. You have, this is your internal virtual work. The sum of this and this is your external virtual work. So ultimately you get this as the weak form. This is also something that we derived for 2-dimensional cases. And now you will introduce the void notation. This is your displacement vector. This remains the same because it was 3 cross 1. Whether you use void or not, it doesn't matter. We transform the strain tensor from a let's say 3 cross 3 matrix to a 6 cross 1 matrix, where these terms are twice the off-diagonal terms. The same thing for stress tensor. It goes from 3 cross 3 matrix to a 6 cross 1 vector. And when you substitute your void notation into your weak form, what you get is this thing. Now this is also something that we did for 2 dimensions. And just a little word about discretization. So these are the different types of elements that we use in 3-dimensional cases. This tetrahedron is very similar to your T3. The same type of shape functions that you had for T3, you can generalize it to this T4 for 3-dimension cases. So just like you had area coordinates in T3, you have volume coordinates. So how many volume coordinates will you have in general? For L1, there are 4 nodes. As you start from the opposite face, go to the opposite vertex, you are increasing L1, right? So the opposite vertex increasing L2 and so on. So you have 4 volume coordinates, and the same type of relationship holds. L1 plus L2 plus L3 plus L4 is 1. Then you also have these nice hexahedrons. These are very convenient to implement. And you have some special types of elements which are prisms. So this is a triangle on the face, and it is extruded to give you something that has 6 nodes. So these are also sometimes used to connect elements, connect meshes of different types of elements. Okay. But essentially, once you have this weak form, once you have this divided up into elements, all that you do is your same finite element approximation, which is shape function matrix times the degrees of freedom vector. So how many degrees of freedom will this thing have? 24, right? So there are 8 nodes. Each node has 3 degrees of freedom, 24 degrees of freedom, which means that your stiffness matrix for this will be 24 cross 24. And your degrees of freedom are 24 cross 1, right? And what would be the size of this B matrix for this one? Six cross 24, right? So there are 6 elements right here. There will be 24 columns in this way. So everything else pretty much remains the same. You calculate your global stiffness matrix by assembly and solve using boundary conditions. And the same sort of errors that we had, error measures that we had before are going to still hold true. So let me actually talk a little bit about these variational principles. Now these are the same sort of energy principles that we talked about in 1 dimension. In 2 and 3 dimensions we did not talk much about this. So okay, in 1 dimension you remember those energy principles, we represented those by pi, right? So let me ask you this, in 2 and 3 dimensions we have this equation that we started with. What procedure did we use to go from here to here? This is the weak form. How did we go? I mean, we just talked about that, but what is that procedure called? Principle of virtual work or method of weighted residuals, right? So we have principle of virtual work or method of weighted residuals. How do we go from G? Let's say if you are given some differential equation, you have found out G. How do we know if there is a pi? So we use the Weinberg theorem to go from G to pi. And not for all types of G is this going to be existing. So we need to make sure that an energy functional exists before we can actually derive it. Now the other way is so this way was starting with the differential equation. But there are quite a lot of problems where you actually start with this. So from some physical principles, you know what is the energy stored in the system, and this is something that we derived for that spring and mass problem, right? So let's say I have some way I know what this energy functional is. How do I go to the this weak form? Right. So we need to minimize this. And to minimize this, we used a directional derivative. So once we have this weak form, how do we find out what is the underlying governing equation? How do we do that? So if you remember, going from here to here, we did integration by parts to balance the derivatives, right? So from here to here, we go again integration by parts, but to unbalance the derivatives. So integration by parts to unbalance the derivatives. And we unbalance the derivatives on u and u prime so that we can, u and u bar, so that we can pull out u bar common, right? And once we pull out u bar common, what we get is the governing differential equation, which is also called Euler equation. Okay, so this is sort of the picture of all this, the big picture of how we are, where all this fits. You can start with your governing differential equation, use the method of weighted residuals or principle of virtual work to get weak form. And if you want to find out whether some energy functional exists, you can use Weinberg's theorem. On the other hand, if you start with pi, you can find out what is, how to implement this on a finite element using this minimization procedure. You can also find out what is the underlying governing equation by using integration by parts to unbalance the derivatives. And that equation in general is called the Euler equation. All right, so for 2 dimensions and 3 dimensions elasticity, the energy functional is a very basic generalization of what you had in 1 dimension. So in 1 dimension, if you remember, you had half. So for the spring model, what is the energy? Let's say I have a spring of stiffness K, um, displacement U. The energy stored is half Ku square, right? So this is exactly that. Half times strain times stress. Stress is K times strain. So this is the energy stored in your system. If you have a 3-dimensional body, if you strain it, this is the energy going to be stored in that body. This is the potential due to external forces. So let's say you have a body force B at every point, or you have a traction at the boundaries. You take your real displacement, multiply it with those body forces or tractions. That will give you the energy, the potential of the system. And another important thing to note here is that energy is a function only of the real displacement. There is no virtual displacement in the energy of energy functional. But the virtual work functional, it has both. It has the real displacement, it has the virtual displacement. Okay. And how do we go from pi to this g? We take the directional derivative, which we know is defined like this. So this is d by d E of this potential energy. So the idea is that you have some potential energy, you are going to perturb it by a small amount E, and you're going to you're going to try to find what is the derivative of that function. This is how we minimize things, right? We take the derivative, set it to 0. So to minimize this potential energy with respect to a virtual displacement, this is the expression that we use. So we are perturbing the energy by this small amount E. It should be E here. So and then all that we have to do is to expand it out, take the derivative with respect to E, and finally set it to 0. You have to take the derivative before you set it to 0, right? And then when you do that, you will get this type of a formula. And if you notice, this is the virtual strain, E or epsilon bar. This is virtual strain. This is the stiffness matrix, or you can say elasticity matrix, elasticity constants. This is the real strain, virtual strain, real strain, virtual displacement, body force, virtual displacement, and tractions on the edge. So this is nothing but your weak form, right? So the reason that we are talking about this variational principles in 2D and 3D is because using this, we can actually impose some types of constraints on our problem. So the idea is, so this is pretty much the last topic in this chapter, and next time we are going to start structural mechanics, like beam theory and plate theory, those kinds of things. I'll also assign, by the way, a final project on Monday, set of maybe 3-4 problems, and we'll go over that a little bit too. So what we are doing is we're trying to find out how to impose constraints on our system. So in general, what the constraint equation looks like is this. You have some displacement. You make some function out of that displacement and set it to 0. So for example, let's say this is a shear wall, and this is connected to a very deep and stiff beam and resting on the floor. And in some shaking experiment, maybe you want to say that this edge must always remain horizontal. So one way to express that constraint is that the displacement, which is a function of x and y, all along this edge on this gamma I, has to has this form, where for every point along this, the horizontal displacement, the vertical displacement should be the same, right? So let's say some constant. So the vertical displacement for every point along this edge must be the same. So this is one way to express a constraint on your system. If you remember, in the end, you will get a k times d minus f. How do you make sure that whatever final answer that you get from your k d minus f satisfies the constraint that this edge remains horizontal? That's what we are trying to talk about here. So that is one type of constraint where you say that a certain displacement in your model has to equal certain other displacement. A different type of constraint is a constraint of incompressible materials. So we've talked about all those plane strain, plane stress problems. If you set your Poisson's ratio to be 0.5, that is an incompressible material, right? There are rubbers under small deformation, they are perfectly incompressible. People who do fluid mechanics treat water as perfectly incompressible, okay? And this is, you can see that actually if you take your code, your homework 5 or homework 6 code, and if you substitute the value for Poisson's ratio as 0.5, actually in your code it might work because it's a plane stress code, but if you write a 3-dimensional problem, take a look at this elasticity matrix. This is the elasticity matrix for the 3-dimensional problem. It has a 1 minus 2 nu sitting in the denominator. You plug into nu is equal to 0.5, this goes to infinity. So you cannot solve perfectly incompressible problems using the procedures that we have talked about. So for those types of problems where you have these constraints, you try to develop what are called these augmented Lagrangian approaches for these constraints. So the idea is that this is there is some potential energy function, and you're going to add something, add a constraint to that potential energy function, and then minimize it. So let's take a look at how that works. So one method is called the Lagrange multiplier method, and to set up this sort of a functional, what we do is we take our potential energy functional, what we had before, and add lambda, which is the Lagrange multiplier, dotted with this constraint equation. So what we have done is we have augmented our function with this new term, and this lambda is called the Lagrange multiplier. And C is nothing but the constraint that you have. So actually, in this case, I should have mentioned this. You have this equation that you want to make sure is satisfied. So one way to do that is this minus this is equal to 0, and this is what you define to be your constraint. This is what Cu is. Similarly, for incompressible materials, the constraint that we usually have is Jacobian, the determinant of Jacobian, which measures how much is the volume change or the area change or length change. That is the constraint, which is a function of u, because Jacobian itself is a function of u. That has to be 0 at every point in the domain. So let's say if I have some sort of a rubber material here, what I'm saying is determinant of J has to be 0 everywhere in the domain. That is a constraint. So to solve these types of problems, what we do is this Lagrange multiplier approach. And let's take a look at this, we set up the equations using this Lagrange multiplier approach. The idea is now you have a modified energy functional. This modified energy functional is now a function of the real displacement and this Lagrange multiplier. So now we need to minimize this to get our virtual weak form, right? So if we have a pi u, we minimize it to get the weak form. So we are going to minimize this with respect to u and with respect to lambda. So when you minimize this with respect to u, what you get is minimization of this with respect to u. That gives you the old virtual work, whatever you had before. And if you minimize this with respect to u, the only thing that you need to find the new derivatives for is this constraint. So what you would get is a new equation that looks something like this. Your kd minus f is sitting in here, and this term is going to lead to an additional sort of force on your system. Okay, and if you take the derivative of this with respect to lambda, lambda only occurs here. This is the Lagrange multiplier which occurs only here. So everything, this term will go to 0. What you will be left with is this Cu is equal to 0. So this is the constraint that you get back by using this augmented Lagrangian approach. And now if you use the same type of techniques, you discretize your domain, use your shape functions, all that stuff, you will get d global transpose, this is the virtual displacement, times k times d. This is something that we had before, the first row. The second row is coming from this constraint. And using this Lagrange multiplier method, you can see that this new matrix will be larger, but it still remains symmetric. Okay, and there is a trouble in solving these types of problems, which you should note here is there is something called BB condition, which is named after two mathematicians, Babushka and Bredzi. So anybody heard of Babushka? No? So yeah, he's a functional analyst from Texas Austin, very established person, and Bredzi is also a functional analyst from somewhere in Europe, I don't remember. But so the idea is that whenever you decompose your problem in such a way that you are imposing an extra constraint, and this essentially becomes a mixed formulation. So for mixed formulations, you have to make sure that your finite element problem satisfies these conditions. And then there are penalty methods, but let me actually stop here. Maybe we'll discuss more about penalty methods next time. And then we'll also start the structural finite elements for structural mechanics problems.